sensor integration architecture for electric vehicles and Python code for motor speed and position sensors. Abstract. We will discuss a detailed examination of the sensors essential for the efficient operation of electric vehicles, EVs. We will address the purpose of each sensor, their key functions, and propose an innovative architecture for seamless integration. By offering a holistic understanding of sensor technologies and their integration, this work aims to contribute to the advancement of EV technology and foster sustainable transportation systems. Introduction. Electric vehicles have emerged as a promising solution to combat the environmental challenges posed by traditional internal combustion engine vehicles. To achieve optimal performance, safety, and efficiency, a wide array of sensors is required to monitor and control various aspects of the EV. In this video, we delve into the key types of sensors used in EVs, their roles, and how to integrate them into a cohesive architecture. A types of sensors and their purpose. 1. Battery Management System, BMS, sensors. Purpose, to monitor the state of charge, SOC, state of health, SO, and temperature of the battery pack. This ensures battery safety, enhances longevity, and optimizes energy usage. 2. Motor Speed and Position Sensors. Purpose, to determine the rotational speed and position of the electric motor. This information is critical for motor control, torque calculation, and regenerative braking. 3. Inertial Measurement Unit, IMU. Purpose, to measure the vehicle's acceleration, orientation, and angular rate. IMUs enable stability control, traction control, and rollover prevention. 4. Proximity Sensors, Ultrasonic, LiDAR, radar. Purpose, to detect obstacles, pedestrians, and vehicles in the vicinity. Proximity sensors aid in advanced driver assistance systems, ADAS, and autonomous driving functionalities. 5. Current Sensors. Purpose, to measure the electric current flowing in various parts of the EV, such as the battery, motor, and auxiliary systems. Current sensors assist in power management and fault detection. 6. Temperature Sensors. Purpose, to monitor the temperature of critical components like the motor, power electronics, and charging system. Temperature sensors prevent overheating and contribute to thermal management. 7. Tire Pressure Sensors. Purpose, to continuously monitor tire pressure and provide real-time feedback to drivers, enhancing safety and energy efficiency. The architecture for sensor integration. An efficient and reliable architecture is crucial for the successful integration of diverse sensors in an EV. We propose the following framework. 1. Sensor Data Acquisition Layer. This layer involves the physical placement of sensors throughout the EV to gather real-time data. Sensor data is collected and pre-processed before being sent to the next layer. 2. Centralized Data Fusion Layer. In this layer, the raw data from various sensors is fused and processed to generate a comprehensive understanding of the EV's current state. Data fusion algorithms handle sensor data integration, reduce noise, and enhance accuracy. 3. Decision and Control Layer. The integrated data is used to make informed decisions and implement appropriate control strategies. This layer governs various aspects, such as power distribution, motor control, regenerative braking, and safety systems. 4. Human-Machine Interface, HMI. The final layer communicates crucial information to the driver through an HMI. It offers real-time insights, warnings, and feedback, enabling the driver to make informed decisions and maintain a safe driving environment. Conclusion. This video has presented an in-depth analysis of the essential sensors for electric vehicles and proposed a robust sensor integration architecture. By leveraging sensor technologies and integrating them seamlessly, EVs can achieve higher efficiency, enhanced safety, and pave the way for sustainable transportation systems of the future. The proposed architecture fosters continued research and development in the field of electric vehicles and intelligent transportation systems. Practical example. Now, we will be creating a complete working motor control algorithm with real-time inputs from a motor speed and position sensor. For this example, we will assume that the motor speed and position are represented as numerical values, and we will implement a simple proportional integral derivative, PID, control algorithm for motor speed control. The context is for a 5.6 kilowatts BLDC motor using NXP architecture with motor speed and position sensors, including resolvers and encoders from Micron Technology. You will need to adapt this outline to your specific setup to cover the following factors. Motor control interface. Before implementing the control algorithm, you need to ensure that you have access to the NXP motor control architecture and the appropriate libraries to interface with the motor driver and sensors. Sensor reading. The code will need to include functions to read data from the resolver and encoder sensors provided by Micron Technology. These sensors will provide information about the motor's position and speed. Control algorithm. For a BLDC motor, you can use a field-oriented control (FOC) algorithm, which is a popular technique to control BLDC motors efficiently. The FOC algorithm requires the following inputs: motor position, from the encoder; motor speed, from the resolver or encoder; current feedback, from current sensors; PID control, optional. You may still use PID control for speed control or current control within the FOC algorithm if required. The gains, KP, key, KD, can be adjusted based on the specific motor and control requirements. Motor driver interface. The code needs to interface with the NXP motor driver to control the BLDC motor. You'll need to utilize the NXP motor control libraries to set appropriate motor voltages or currents based on the control algorithm's output. Here's the code. Base code A. Pause and see the code. Base code B. Pause and see the code. Base code C. Pause and see the code. Note: check the comments section for a copy of the complete base code. Please note that this code outline is not a complete implementation but rather a guideline to help you get started. For accurate implementation, you'll need to refer to the documentation and libraries provided by NXP and Micron Technology for interfacing with their respective hardware components. Additionally, you may need to adjust the control algorithm and motor driver interface based on the specific requirements of your motor and application. If you have enjoyed it, please like, share and subscribe to my channel at Ahamevyaham.